Hello, everyone. Thanks for attending the talk. This is joint work with my advisors, Sid Banerjee and Chris Iyer. And this is work about allocation of goods without money. There are many practical settings where resources are allocated without money. Think about firms or universities allocating computing resources to employees or students, allocating medication, aid, parking spots, course seats, and so on. And the question we're interested in is how to ensure efficiency and fairness without introducing monetary payments. One particular class of allocation without money is dynamic allocation. So when allocation is repeated, this essentially gives the designer more degrees of freedom to do non-trivial things. If you only allocate once and you don't really know the preferences of the agents, essentially the only fair thing you can do is lottery. Whereas if items or resources are allocated repeatedly, you can do things like give someone less today and they may give them more tomorrow. You can also leverage future allocations as an incentive for agents to reveal their preferences truthfully now, so as a proxy for money. And so there's a more non-trivial space of mechanisms to use. It's also quite practical, so most of the examples I listed on the previous slides are in fact dynamic allocation. One particular class of dynamic allocation mechanisms we're particularly interested in are artificial currency mechanisms. So the idea is quite simple. You don't have money. What's the next best thing? Well, you print money, artificial tokens, you distribute it between the agents, and you get them to bid on the items using those artificial tokens instead of money. This approach was actually realized in practice. The most famous example is a nonprofit called Feeding America, which is responsible for distributing donations from food donors, such as supermarkets, to different food banks. And a while ago, a couple of economists came into the picture and redesigned the system using artificial currency mechanism and actually improving the efficiency of the system by quite a bit. One of the metrics being the amount of food wasted, which has gone down, which in turn incentivizes the donors to donate more since it's not getting wasted. And so the question we're interested in is this approach seems to work in practice, but theoretically, what are the incentive and efficiency properties of such mechanisms that we can establish? And to do that, we start out with a very simple model, and later on in the talk, I'll talk about some generalizations for it. But for now, we have n agents and t rounds. So on every round, you're going to allocate a single item. This item is divisible. Every agent has some value, VIT, for every item, so it can depend on time. And utility of the agent is given by just the sum of values times allocations this agent has gotten. The mechanism here just listed some reports from the agents and then chooses the allocation, which can depend on reports and the public history of what happened previously. Finally, we'll use something called ideal utilities as a benchmark for efficiency, and I'll talk about this in a couple of slides. So now we need to define the mechanism, and as I described before, we are going to use artificial currency auction, namely first price auction. So the mechanism is very simple. We're going to give each agent some budget BI, and then at each turn, agents are going to submit their bids, and the highest bidder is going to pay, meaning their budget is going to get updated accordingly and get the item. This is a pretty simple mechanism, but it induces a complicated game, equilibrium of which is hard, if not impossible, to characterize. So a couple of intuitive reasons for this is because the game is budgeted, agents have incentive to bankrupt each other, so make other agents run out of money. Also, because it's a repeated game, equilibrium of such a game can contain things like threats or collusive behavior, and this is why it's so hard to find the equilibrium. And yeah, finally, I need to talk about our benchmarks before describing our results. We use something called ideal utilities, and our goal in finding fitting benchmark was understanding what utility profiles can occur as the outcome of a mechanism. This is in contrast to the approach of using social welfare. We sort of aggregate all the utilities into a single number. And we don't want to do this, one reason being that in an absence of money, comparing utilities may not be very meaningful. Also want to give guarantees for individual agents rather than collective as a whole. And so we use something called ideal utilities, which I will first illustrate and then define formally. So here we have a couple of agents and 4 rounds, so 1 item on each round. These agents have some values for each item. And once they learned all of their evaluations, so after the allocations are made, we can approach those agents and ask them, hey, you can only pick half of the items that were in the game. Which ones would you prefer to pick? They'll pick items with the highest valuations, and as a result, they'll get some amount of utility, so 5 and 7 correspondingly. And those numbers we essentially call ideal utilities. So ideal utility here is basically the value you get from your favorite items, but the number of items you can get is only your fair share of the items. By the way, note that those 2 agents cannot actually simultaneously obtain their ideal utilities because one of the item is included in both of their favorite item bundles. So formally, we define something called endowments, which can be interpreted as a fraction of the items you have a right to. And given those endowments, so there's a single number alpha I for each agent, we define ideal utility as the maximum expected utility an agent can get under any allocation rule, such that in expectation, this allocation rule equals to alpha I. For simplicity, you can think of alpha I equaling 1 over n, which corresponds to the setting of equal endowments. So if agents have equal rights to the item, for the reasons, alpha i's are 1 over n, and then your allocation rule constraint is that expectation of xi equals 1 over n. This definition is pretty easy to generalize to many items. As I mentioned on the previous slide, generally this utility profile given by this definition may not be simultaneously feasible for all agents because they may compete for some items. So it's, in a sense, even too good. And also for any Pareto optimal outcome, there's ideal utility profile that dominates that Pareto optimal utility profile. So if we approximate ideal utilities, we're also approximating Pareto optimal utilities. Finally, we need to talk about incentives. For incentives in this work, we're using maximum value. I'm sure many of you are familiar with it. So maximum value is defined as a maximum expected utility an agent can get under worst case strategies chosen by other agents. So there's an adversarial model. And given that our sort of final guarantee that combines maximum value with ideal utilities is something we call beta utopia. So we say that the mechanism satisfies beta utopia for some endowments alpha I if maximum value of every agent is at least a beta approximation of corresponding ideal utility. So no matter what everyone else does, you can get at least a fraction of your ideal, beta fraction of your ideal utility. We do in fact show that the mechanism we defined before, artificial currency first price auction, satisfies a half utopia if you set budgets proportionally to the endowments. So your alpha i's essentially set the ideal utility profile you want to approximate, and if you pick budgets proportionally to that alpha I, you're guaranteed to in fact approximate those ideal utilities. One thing to note is that we have a 1/2 minus O of 1 approximation. So what it means is that as a number of rounds t goes to infinity, you converge to 1/2. But say if you have only 1 round, you essentially can give no guarantees. Those are very robust guarantees in that you don't need agents to converge to Nash equilibrium. Every agent can obtain their ideal fraction of their ideal utility no matter what everyone else does. Also, by ensuring this, we're guaranteeing approximations of Pareto optimal outcomes. There's also equivalent price of anarchy guarantee if you care about Nash equilibria, as well as if you care about some aggregation welfare function. As long as it's linear, you're also approximating that. I'll now go through a proof sketch for this result. So essentially what we're trying to do is establish a bound on the maximum value for this game. And the way you would go around this, you need to establish this bound, and you can go about this by picking some strategy, some good sounding strategy A for the agent I, optimizing for the adversary. And it's actually not that hard to find a strategy that sounds good and seems to work for agent I. For example, you can think, what if you bid proportionally to your value, right? The tricky part turns out to be computing optimal adversary response.
because the game is dynamic, it is essentially intractable for most strategies that you can come up with. So what we end up doing is constructing a strategy that is simultaneously so simple, it's actually possible to construct optimal adversary response, but at the same time, it's good enough to actually provide you good utility guarantees. We call this strategy Bernoulli strategy, and the way we proceed with the proof is we essentially show with this strategy that the utility you get from it is proportional to the amount of money you spent. And we also show that the adversary cannot really prevent you from spending money if you play according to the strategy. To go through these steps more slowly, let's start out by defining the strategy. So the way we define strategy is you either bid 0 or some constant value rho, and you only bid rho if your value for the item is high enough, specifically if it's high enough so that the item is in your ideal allocation according to the ideal utility definition, which you're going to do with probability alpha I. So think of alpha I in the sort of symmetric case being 1 over n, then essentially you're bidding something constant with small probability, and otherwise you bid 0. And the intuition behind the strategy for like why it works in an adversarial setting is that if you're bidding with a small probability, it's expensive thing for the adversary to prevent you from winning the item if you do end up bidding, because most of the time the adversary will try to block you and bid something, but actually you bid 0, so they'll spend money for no reason. And it only works for first price option. The same trick does not work for second price option because adversary can prevent you from winning without spending too much money. And it's actually not quite hard to generalize this to many items. Secondly, for this Bernoulli strategy, we show following bang for buck lemma. Essentially, what it says is that the utility of an agent who adopts this strategy is lower bounded by a linear bound in their spending. So the more you spend, the more utility you get. And this bound has rho in it. I'll remind you, rho is the amount you bid, the constant amount that you bid in your strategy. So if you have a bigger rho, you're bidding more, then it's harder for the adversary to prevent you from spending. They'll have to bid more as well, but also your trade-off gets worse between utility and spending. So the question is, what's the optimal trade-off here for what's the amount you should bid in the Bernoulli strategy? And for this part, we also have spending lemma. So now that we have established the bang for buck lemma, we can essentially forget about utilities and only worry about spending. So agent I has some budget, and they play a Bernoulli strategy, and adversary now wants to just prevent agent I from spending their budget, as much of their budget as possible. And the result what we establish is that under optimal play of adversary, agent can spend a certain amount that depends on the amount they bid, the rho. Specifically, when rho equals 2, the adversary cannot prevent agent from spending most of their budget, which in turn implies that they cannot prevent them from getting a certain amount of utility. Rho equals 2 actually turns out to be the optimal trade-off between spending more and getting more utility per unit spent, and it establishes the main result of the theorem that I stated before. Before we move on to generalization, one more point I wanted to make that sort of follows from this proof for the result we established is that it's not just theoretical that the agents can in practice can get this amount of utility. It's quite easy to imagine that in practice, if this mechanism is implemented, people are able to secure this utility because the strategy that is needed to do so is quite simple and intuitive. Essentially, what Bernoulli strategy does is if you have high value for something, you bid, otherwise you don't. And it's easy to imagine people adopting something like this in real life and correspondingly getting their ideal utility approximations. But yeah, moving on, we generalize our results to a setting with many items. So what changes here is on a given round, there are not one, but many items people compete for. And the valuations agents have for many items are nonlinear. They could be as general as XOS valuations, which is a
General class evaluations is defined as a maximum of k-linear evaluations and includes modular evaluations. So it is quite general in class. We show similar results. I'll talk briefly about this. So first of all, how do we generalize our mechanisms? The most straightforward thing is to still keep running first price auction, but for every item individually. You still endow agents with budgets of artificial currency, and you run the separate first price options. Slightly more complicated generalization that turns out to have more generality to it is something we call chromatic auction, where you actually issue several budgets of different artificial currencies. So think of it as currencies of different color, where every color corresponds to a certain item type. You still run first price auction for every item, but using corresponding currency and corresponding budgets. Finally, I need to say a few words about generalizing ideal utility. So we used to use endowments alpha i's, which could have been interpreted as basically what fraction of the items you expect the agent to get at your ideal outcome. Now, alpha ij is a matrix where you can interpret alpha ij as like what fraction of item j you want agent I to get in the ideal outcome. And given that, it's quite easy to generalize the definition of ideal utility itself. Namely, it's the maximum possible utility agent can get while getting at most alpha ij fraction of item j in expectation. So given all that, we can state our results for many items. Namely, we show that the mechanisms that I stated satisfies half utopia for endowments alpha ij. The distinction is that the more complicated chromatic auction that uses multiple currencies can do so for arbitrary endowments, whereas the simultaneous first price auction that only uses one budget and one currency can only provide this guarantee for uniform endowments, meaning that endowments are equal across items, which you can imagine being true and practical in many situations, but maybe in others it isn't. And that means you have to use more complicated mechanisms. To wrap up, we show that there are robust incentive guarantees for allocating resource using artificial currency for payments. The mechanism is simple to implement, intuitive to play, and prior independent, meaning that the agents do not need to know distributions of values of other agents, neither does the designer. And finally, when the designer picks the budgets to allocate to the agents, this can be interpreted and viewed as the designer deciding what fraction of the items they want to give an agent to get in the ideal outcome, and then approximate that ideal utility profile. This is all I had for you. Thank you for your attention.